All right, welcome everyone to this video on Chapter 11, in which we're going to be talking about inferences for population proportions. All right, to set the scene a little, in our previous chapters, was Chapter 8 through 10, we talked about methods for finding confidence intervals and to perform hypothesis tests for a one or two population means. Right, so that's what we concentrated on. Now we're going to move on to doing the exact same inferential method, so to conduct those inferences for population proportions. Right, so as we move forward in this section here, we're going to be using example 11.1 as our motivating example. So we're going to use this to introduce the notation and terminology necessary to perform the proportion inferences that we've been talking about. All right, so starting with example 11.1, campus legend tells the story for two friends who lied to their professor by blaming a flat tire for having missed an exam. Right, so a professor then sent them to separate rooms to take a makeup exam. The first question was quite easy and it was worth 5 points. The second question, worth 95 points, asked which tire was it. And remember, they're not allowed to communicate with one another. So the question is, if you were caught in this hypothetical situation, all right, let's hope so, and you suddenly had to choose between a hypothetical flat tire between 4 tires, front left, front right, back left, back right, which one would you pick? All right, so unfortunately, we're not in class, so I can't have you fill out a survey. But it was speculated that people would pick the front right tire more often, right? So when I did this survey previously, we found that 47 of the possible 118 said front right tire. All right, and what we are going to do is we're going to make inferences based on this information here. So the first question is, what proportion of the people that answered that question picked the front right tire? Well, proportion is going to be the number of outcomes, in this case picking front right tire, divided by the total number of outcomes, which is 118. And that comes out to roughly 0.398. All right, so this here is the proportion from our sample here. We picked a sample of 118, and the proportion coming from a sample we're going to be denoting by p hat. All right, so this is sample proportion. All right, so if it is a sample proportion, this is a statistic because it's coming from a sample. All right, and the notation we are going to be using for the population proportion will be lowercase p. All right, so p will denote population proportion. All right, also referred to as true proportion. And since this is pertaining to the entire population, this is going to be a parameter. And the goal is, again, what we would like to do is we are interested in making inferences about the parameter in question using statistic, right? So again, we are interested in making inferences about our parameter using our statistic. All right, so again, what we're going to do is we are going to compare this with what we've been doing so far, which is, so far we've been making inferences about the population mean using our sample mean. So the first thing we really needed to know, remember, to make inferences about the population mean based on the sample mean, we needed to know what the distribution of X bar was like. All right, so in other words, what we needed to know here was we needed to know what the sampling distribution of the sample mean looked like. All right, and so we want to understand the distribution of X bar, just like we wanted to understand the distribution of X bar. In this particular case here, we'd like to understand the distribution of the sample proportion. All right, so in other words, we are interested in understanding the sampling distribution of the sample proportion. When we're talking about distribution, there's three things we would like to know. The first thing is we'd like to know what the center is, or the mean is. And the mean of p hat is going to be p. All right? So in other words, what we are saying here is the mean of p hat equals the population proportion. The standard deviation of p hat is going to equal this quantity here. So it's going to be p times 1 minus p divided by n. So we know the center here, and we know what the spread here is as well. Spread is the standard deviation, and I want to point out we know sigma, not s here. And finally, we know the center, we know the spread. Now we'd like to know the shape. For large N, p hat is approximately normally distributed. All right, so we have our own version of a central limit theorem here for sample proportions as well. So we know what the shape looks like. All right, so those are the three things we need to describe if we want to talk about the distribution, general shape. We need to know the center, the spread, and the shape, and we know that. All right, so to summarize what we have said here, so in other words, if our N is large enough, all right, so N being the total sample size, then the possible sample proportions for the samples of size N have approximately a normal distribution with a mean of p and a standard deviation of square root of p times 1 minus p over n. All right, so at this point, a one word of caution: it is very, very easy to mix up the proportion p with the p-value. I know, but just be careful. So that's why in this class here, if you go back, we have been using uppercase p for p-value, and we are going to use lowercase p for proportion, even though in my writing it's very, very difficult to distinguish between those two there. All right, so now that we know what the distribution of p hat looks like, we can go ahead and talk about how to make inferences about the population proportion based on the sample proportion. And the first thing we're going to be talking about is we're going to be talking about the confidence interval. So let's say we know the sample proportion for a given quantity we're interested in, and what we would like to do is use that information to find the confidence interval for a population proportion. All right, so the assumption we are going to be working with first is that our sample be simple random sample. And next is the number of successes, which we're going to denote x, and the number of failures, which we're going to denote n minus x. So it's going to be the total number minus the number of successes, should both be greater than or equal to 5. So in this case here, successes is going to refer to the quantity we're interested in. So for instance, in this particular example that we have in mind, successes would be front right tires. So in this case here, a front right tire we said was 47, so that's bigger than 5, right? And n minus x, which is 114 minus 47, and that's bigger than 5 as well. All right, so once those two quantities, those assumptions are satisfied, the confidence interval computation for confidence interval is going to be the step-by-step method here described below. First, we're going to figure out what the confidence level is, and then we're going to use our table to find z alpha over 2. Right? So again, in this case here, remember we know sigma. When we know sigma, we work with z rather than t. And z is the easier one to look up the table for. All right? So once we find our z alpha over 2, remember the confidence intervals are always of the same form, roughly. It is observed value, right? So it's observed plus or minus our test statistic, which in this case is z, times the standard error. So though that formula gives us the endpoints for the confidence interval, and it's the same thing here, we are going to use our sample proportion, which we observe, plus or minus our test statistic, times this quantity here is our standard error. All right, so, and finally, once we have our confidence interval, we are going to go ahead and interpret the confidence interval. So let's go back to our example earlier. What we'd like to do is we'd like to determine and interpret a 95% confidence interval for the population proportion of all people who picked the front right tire. Right, so again, the assumptions for our confidence interval, the sample is simple random. So I'll have you trust me that it is simple random, and we've checked that the second assumption holds as well. So once we know that, we are going to go step 1, which is going to be looking at our alpha. So since we're looking at 95% confidence interval, our alpha is 1 minus 0.95, which is 0.05. So we're going to be interested in z alpha over 2, which is z of 0.025. And this quantity here is going to equal 1.96. All right, so if you are not confident, I would go back and remind yourself on how to look up z tables to find these values here. All right, so now that we have that, our step 2 is going to be finding the endpoints of the confidence interval. And remember from earlier, our p hat was 0.398. That was the proportion of people in our sample that picked the front right tire. So once we know that, the endpoints of our CI, or the confidence interval, so the endpoints of our confidence interval are going to be, again, the observed statistic plus or minus z alpha over 2 times the standard error, and which in this case here is p hat 1 minus p hat divided by n. We are going to go ahead and plug in these values here, and when I do that, I'm going to get 0.398 plus or minus 1.96 times this 0.398 1 minus 0.398 divided by the total number, which was 118. And if I plug this into my calculator, I'm going to get 0.398 plus or minus 0.088. So the confidence interval is going to be an interval. So our 95% confidence interval, so our 95% confidence interval is an interval, and the left endpoint of that interval is 0.310, and the right endpoint of that interval is 0.486. All right, so this is what we call the interval notation, and when I write this notation here, what that means is this is an interval whose left endpoint is 0.310 and whose right endpoint is 0.486. So this interval here contains all numbers between these two numbers here. So anything in this interval is greater than 0.310, but less than 0.486. Right? So this is a way of expressing an interval. So this really is another way of writing from 0.310 to 0.486. So that's our 95% confidence interval. So step 3 is interpret the confidence interval. So in this case here, what that means is we are 95% confident that the proportion of population, that the true proportion that would pick the front right tire is between 0.31 and 0.486. All right, so we are 95% confident that the true proportion that would pick the front right tire is between 0.31 or 0.486. In other words, we expect, with 95% confidence, we can say the proportion, that between 31% and 48.6% of the population would pick the front right tire. All right, so if we go back to this question here, it says provide an interpretation of what is meant by a 95% confidence in this context here. All right, so it's been a while since we talked about what confidence intervals are, but remember, 95% confidence means that if we took a large number of samples, all right, so if we took a large number of samples and we calculate the confidence intervals for all of those samples there, we would expect 95% of them to contain the true population proportion. That's what it means when we say 95% confidence. All right, let me repeat that again. What that means is 95% confidence means that if you took a large number of random samples and you calculated the confidence interval for all of them, right? So as soon as you pick a different sample, your proportion might change, which means your confidence interval is going to change as well. However, if you took a large number of those, then you would expect 95% of those intervals that you've picked to contain the true population proportion. All right, so that's what it means when we're talking about 95% confidence. All right, so that's the confidence interval. Now what we would like to do is talk about performing a hypothesis test. All right, so confidence interval, as we've talked multiple times and we're going to keep talking, there's a big relation between hypothesis testing and confidence intervals. But the goal here is, in this page here, you'll see a step-by-step description on how we're going to perform a hypothesis test for a population proportion. All right, so the first thing is going to be state the null hypothesis. So we're saying the population proportion is equal to some fixed value P naught. And the alternative hypothesis, again, is going to come in three different flavors. One of them is two-tailed, where P is not equal to that fixed value P naught. Left-tailed, where the population proportion is less than that specified value P naught. And alternative hypothesis is where P is bigger than P naught. All right, and the reason I jumped into step one here before talking about the assumptions is, as usual, we are talking about simple random sample here. But the second condition that we need to satisfy is the following. N, remember, is the sample size. We need both N times P naught. This P naught here being the hypothesized value of our population proportion, and N times 1 minus P naught should be both bigger than or equal to 5. All right, so this P naught here that we are talking about in our assumption is our hypothesized population proportion. After that, the test is going to go on the same way. So we are going to decide on a significance level, alpha, and then we are going to compute the value of our test statistic. All right, so let's go on. P hat here is our sample proportion. P naught here is our hypothesized value of the proportion. And let's look at the denominator. And I want to for you to pay attention here. The denominator here is not P hat, but instead P naught, which is the hypothesized value. So when we are computing the standard error, which is in the denominator, we are using the hypothesized value, not the sample proportion. The reason we're doing this is, remember, when we are doing a hypothesis testing, what is the assumption we are making here? We are assuming that the null hypothesis is true. which means when we start our hypothesis testing, we're working under the assumption that our population proportion is equal to P naught. So that means when we're computing the standard error, we are going to use the hypothesized value for our population proportion and not the sample proportion. All right, so this is something I wanted to highlight right here. Once we have our test statistic, since depending on whether it's two-tailed, left-tailed, or right-tailed, we're going to find the p-value, which again is going to be the area under the curve. And step 5 is if p is less than or equal to alpha, reject h naught, otherwise we don't reject h naught. And finally, the most important thing is interpret what this means in the context of our hypothesis test or in the context of the question we're looking at. All right, so again, it's very similar, and I have mentioned this a few times already, but the logic behind hypothesis testing is going to stay the same. Again, the statistic we use might be different, right? So the question we're trying to answer might be one population mean, two population mean, or in this case, proportions, but the logic at the heart of it is going to be the same. Find the null hypotheses, state the null hypothesis and alternative hypothesis, and find the probability of getting a sample as extreme as the one we have under the assumption that the null hypothesis is true. And once we have that probability, compare that with our significance level. All right, and that's going to tell us whether to reject or not reject h naught. All right, so there's one thing I'd like to point out here. So what we're going to realize is when we are doing hypothesis testing, it's not always that the significance level is going to be specified. Right? So in certain examples, the significance level will be specified. In certain ones, they will not. If there's no significance level specified, we will go ahead and do our hypothesis testing at 5% significance level. All right? So this is the standard level of significance that has been agreed upon to justify a claim. So that's what we're going to stick to. However, I would like you all to get in the habit of commenting on the outcome of the test for other standard significant levels. All right. So once you do it for 5%, also keep an eye out for what would happen if you did the hypothesis testing at 2.5% and 1% as well. All right. So that's just for our own sake. But again, if there's no significance level specified, the agreed upon significance level is 5%. All right, so now that we have talked about hypothesis testing in the case of a one proportion, what we're going to do is we're going to go back and look at the example we were looking at earlier, which was the tire that we are guessing. All right, so the question states, if there's nothing special about the front right tire, what proportion of people will select that tire if a very large population is asked this question? In other words, what is the probability that a person randomly chooses the right front tire? Right, so it has been conjectured that more people tend to pick the right front tire than you would expect by random chance. All right, so first question here is, what is the probability? So remember the law of large numbers when we're talking about probability. When we're doing this, what is the probability? The probability of an event happening is if we were to repeat this a large number of times, approximately how many times would we expect a person will select the right front tire if there's nothing special about it? So how many options do you have for tires? Well, there's front left, front right, back left, back right. So there's 4 of them, right? And there's one front right tire. So that's the probability that a person randomly chooses a front tire. So now, given that probability, what we would like to do is we would like to look at the following conjecture, do a hypothesis test, in that it has been conjectured that more people tend to pick the right front tire than you would expect by random chance. So by random chance, we would expect the proportion of people that pick the right front tire to be 1/4. So in this case here, step 1, our null hypothesis is going to be that the population proportion is 1/4 or 0.25 in decimal. All right, and our alternative hypothesis. Remember, it is conjectured that people pick the right front tire more than you would expect. Sorry, more people. Yeah. So in this case here, our alternative hypothesis, which we believe it to be true, is P is bigger than 0.25, and it's upon us to find evidence to reject the null hypothesis in favor of alternative hypotheses. All right, so again, we said this is a simple random sample, and the next thing we want to check is whether our assumption is satisfied. Our P0 in this case here is 1/4, and our N is 1/18. So if you do N times P0 and N times 1 minus P0, you're going to see that both of them are bigger than or equal to 5. So the assumptions for our hypothesis test are indeed satisfied. All right, so now step 2 is we are going to state our significance level. However, in this particular example, no significance level has been specified, which means we're going to be working with alpha is equal to 0.05. All right, so next up, step 3 is we want to find our test statistic. Remember, our sample proportion from the sample I gave you earlier is 0.398. And now our z value is, let me write down the formula once, it is going to be p hat minus p0, the entire thing divided by p0, 1 minus p0, the entire thing over n. Again, this p0 here in the denominator is not the sample proportion, it is our hypothesized value. And if I do this here, I'm going to get 3.71. So that's my z-score. All right, so step 4 is going to be go ahead and find the p-value. So again, we are always going to draw our picture because the pictures really help. All right? So we're looking at our test statistic is 3.71. So now we have a right tail test. Right? So when we have a right tail test, we are interested in the area to the right of our test statistic. All right? So right tailed, since we have greater than, we are interested in the area of all test statistic bigger than ours. So this is the one we are interested in. The area to the right, right? And if we look at our table here, we're going to realize that this area is quite small. It is 0.0001. So our p-value in this case here is 0.0001. Now, once we have our p-value, step 5 is going to be, let's go ahead and figure out whether we're going to reject H0 or not. So that means we're going to compare our p with alpha, and p is clearly smaller than our alpha, 0.05, which means we're going to reject our null hypotheses in favor of our alternative hypotheses. All right, so reject H0, accept HA. So what does this mean in the context of our example? That means that 5% significance level, so there's enough evidence to show that more than 1/4 or quarter, right? So more than a quarter of the population chooses the front right tire. All right, so that's it. But again, so let's go through the process here. State the null and alternative hypothesis. Since no significance level was specified, we're going to use with the common standard agreed upon significance level, which is 5%. Go ahead and find the test statistic. Once we know the test statistic, since we are looking at a right tail test, we had p bigger than 0.25. That means we're going to look at the area to the right of 3.71. And if we look at our z table there, we see that the area to the right of 3.71 is the same as the area to the left of negative 3.71, which from the table is 0.0001, which is less than our significance level, so we're going to reject H naught in favor of HA. All right, so at 5% significance level, there's enough evidence to show that more than a quarter of the population choose the front right tire. But like I said earlier, I still want you to see what happens at 2.5% and 1%. So at 2.5%, our P would still be less than alpha, which is 0.025, so we would still reject H naught, and the same thing is true for 1%. All right, so there's really strong evidence to claim that more than a quarter of the population choose front right tire.